Have you ever watched the glowing tip of a sparkler as someone twirls it in a perfect circle? Though the speed may look steady, the motion is far from simple. Welcome to the world of uniform circular motion, where the direction is always changing, even when speed isn't. In this type of motion, an object travels in a circular path while maintaining constant speed. But since the direction of motion continuously changes, so does the velocity vector, making this a case of accelerated motion. Even though the speed remains fixed, the velocity vector undergoes constant change in direction. And as we know, any change in velocity, whether in magnitude or direction, implies the presence of acceleration. This acceleration has a very specific behavior. It always points towards the center of the circular path. This means there's a force constantly pulling the object inwards, otherwise it would just fly off in a straight line due to inertia. As seen in the diagram, we represent the motion using vectors for position and velocity at two different points. The circular trajectory and changing tangents give us a visual clue into the hidden force acting underneath this graceful motion. Now let's understand something fascinating, the direction of this acceleration. If you observe two instantaneous velocity vectors, let's call them v and v prime, at nearby points on the circular path, you'll notice a small angle between them. The change in velocity, or delta v, lies along the direction pointing between these vectors. As the time interval becomes smaller and smaller, the change in velocity becomes instantaneous acceleration. And guess what? It always points towards the center of the circle. This is known as centripetal acceleration. The word centripetal literally means center-seeking. In the diagram, you can see how the vector representing acceleration cuts straight into the center even as the object continues moving around the edge. So, despite having constant speed, the object is always being nudged gently but consistently toward the center of the circle. Now, let's get mathematical. How do we calculate this centripetal acceleration? Imagine a very small angular displacement along the circular path. For such a case, we can assume the arc length to be almost equal to linear displacement, which is speed multiplied by time. Now, consider the triangle formed by the two velocity vectors and their change. This triangle is similar to the one formed by the position vectors. Using this triangle's similarity, we get acceleration equals v squared divided by r, that is, a equals v squared by r, where v is the linear speed and r is the radius of the circular path. This tells us that centripetal acceleration increases rapidly with speed because of the square and decreases with a larger radius. It's like how tight corners require stronger turns. The sharper the circle, the more intense the inward acceleration needed. Let's now bring in a new player, angular speed, represented by omega. When an object moves around a circle, it covers some angular displacement measured in radians. If this angular displacement is delta theta and time taken is delta t, then angular speed equals delta theta divided by delta t. Now here's the connection. Linear speed, or v, is related to angular speed and radius. The formula becomes v equals omega into r. This bridges our understanding between how fast an object spins in angle and how fast it moves along the path. Even if angular speed stays constant, the direction of the linear speed vector still keeps changing, bringing us back to the necessity of centripetal acceleration. As seen in the diagram, the object moves with a linear velocity tangent to the circle, while angular velocity governs its rotation. Let's now rewrite the centripetal acceleration using angular speed. We already have v equals omega into r. So plugging this into our earlier formula equals v squared by r, we get a equals omega squared into r. This version is extremely useful when you know how fast something rotates, rather than how fast it moves linearly. But wait, there's more. Suppose we know the frequency of revolution, that is, how many times per second the object goes around the circle. Then, omega equals to pi into nu, where nu is the frequency. Substitute that back and we get a equals 4 pi squared into nu squared into r. This version of the formula appears often in real-life applications like washing machine drums, satellites, and even fan blades.
Let's apply all this to a real example. An insect is moving inside a circular groove of radius 12 centimeters. It makes 7 complete revolutions in 100 seconds. First, we calculate angular speed. Omega equals 2 pi into 7 divided by 100, which gives approximately 0.44 radians per second. Now, using the formula V equals omega into r, we get V equals 0.44 into 12, which is about 5.3 centimeters per second, and the acceleration a equals omega squared into r, which equals 0.44 squared into 12, giving us around 2.3 centimeters per second squared. Notice that even though the insect maintains a constant speed, it's continuously accelerating inward because of the change in direction. That's the magic of circular motion. Let's quickly recap what we've learned about uniform circular motion. An object moving in a circle at constant speed is still accelerating because its direction is always changing. This centripetal acceleration pointing towards the center is what keeps the object on its circular path. It's given by a equals v squared by r, or a equals omega squared into r, or a equals 4 pi squared into nu squared into r. You'll see uniform circular motion all around you, from satellites orbiting Earth to amusement park rides, and even the motion of electrons in certain atomic models. Understanding this concept is crucial in physics. It bridges motion, force, and the idea of directionally changing vectors. I hope you now see circular motion not just as spinning, but as a beautiful balance of speed and force pulling toward the center. See you in the next session with another fascinating concept of physics.